It is truly a pleasure to be here with so many friends, so many current and former members of NCLD's Professional Advisory Board, and so many colleagues, and to represent NCLD as a co-sponsor of this event. I'm not going to talk about NCLD. Hopefully all of you know the work that we've been doing over the last 40 years. Connecting with me during the conference, please. My colleagues at NCLD, Lindsay and Megan, Melissa and Thomas are all here. Talk to us about what we're doing with our understood.org website. We have a new educator initiative that we're launching. We're doing some really exciting work in personalized learning. We've just hired a new director of young adult initiatives. We are very eager to explore opportunities to collaborate and connect with you all. As someone who dipped his toes into graduate work at Teachers College in Neurosciences and Education back in the 1980s, it really is a distinct honor for me to be introducing John Gabrieli. John's work is at the forefront of understanding the structural and functional differences in brain that define risk and explain struggle for those with neurological and psychiatric diseases, as well as disorders of reading and math. His imaging work has helped us understand what we're seeing in children when they try hard and fail to make progress, and is paving the way to earlier recognition and better options for instruction and intervention. John is Grover Herman Professor of Health Sciences and Technology and Cognitive Neurosciences at MIT. He is the director of the Martinos Imaging Center at the McGovern Institute for Brain Research, and has appointments in Harvard Graduate School of Education and the Department of Psychiatry at Mass General. He has multiple publications on the brain basis of dyslexia and is now studying the relation between reading and math difficulties in brain. My pleasure, John Gabrieli.
Thank you for that kind introduction. It's an honor to address an audience from whom I've learned so much and have followed in so many footsteps, including especially Jack Fletcher, Gwenna Eden, other people here whose work is so foundational in our field. But my entire career, I've, let's see if I'm doing this right, just been impressed, as you have been, by the fragile power of the human brain, that it endows us with every remarkable capacity we have in thought, emotion, feelings, and yet for every strength it has the vulnerability that we recognize in learning difficulties and learning disorders. And so if we're able to attend and focus our attention, we're able to have attention deficit disorder. If we're able to invent print to make spoken language visible and ultimately make it the centerpiece of our educational system, we're able to have difficulties in learning how to read. And so I think of infants as born into this world in a neurobiological lottery, where they will be born with genes that make it easier or harder to navigate the world, born into environments that make it easier or harder to navigate the world. And we know that many children will find the navigation difficult. So we heard that where you define the number of children with dyslexia depends on your choice of cut line, but something 10–15% is a good estimate. 11% of children with ADHD, 1 out of 42 boys with autism, 1 out of 8 children in special education in the US. These problems exacerbated and made more complex by opportunities of education that are difficult under conditions of poverty. 1 out of 5 children grow up in the US in poverty. Half of children qualify for free and reduced lunch. So there's combinations of things in the environment we live in, the genes we're born with. And of course, for reading in particular, as Jack pointed out and others have as well, that reading is a cultural invention. And so, whereas 2,000 years ago, nobody was dyslexic for all practical purposes. We've invented a world in which reading is essential to educational progress, to a sense of agency and efficacy in children. And so, they have to navigate the world they're in and that we have constructed. And with neuroimaging, we're able to understand the brain bases of these differences, these learning differences, and think about both why they occur and what we might do to help children do better. So we've already heard a beautiful description from Jack about the developmental dyslexia. And I want to make the following basic points today and then go through them. First, to a first approximation, there's remarkable consistency in understanding brain differences that occur in the majority of children with dyslexia. Children vary. There's different reasons why children end up reading. They vary in the additional problems they have. But I also work in the areas of attention deficit disorder and autism. There's nothing like the relative consistency that we've discovered in the brain imaging of reading difficulty. There's much more understood than other domains. Second, these brain differences are evident before children get their first moment of reading instruction in school. This means not only does it not necessarily a product of reading, poor reading instruction, which does occur, but most children have this brain difference before a teacher gives the first lesson to the child. And that promotes the possibility of early identification and intervention. There's other ways we're approaching it. It has to be combined with behavioral things and educational policies and practices. But the brain signals are there before, at the very earliest stages. I'm going to share with you one finding suggesting a thought about what leads to the difficulty in phonological awareness in terms of brain plasticity. And then end with two studies talking about prediction and variation that we think might relate to what kinds of interventions might be helpful for children. So this is a slide from my colleague Nate and Gab, which summarizes research from many different researchers that are, to a first approximation, quite consistent compared to practically every other neurodevelopmental disorder, all of which are complicated disorders and variances. So this is showing you areas that show differences in brain structure, predominantly in the left linguistic reading hemisphere, in the ventral pathway, the bottom pathway through the temporal lobe, the superior pathway through the parietal lobe and frontal cortex. In the white matter pathways that connect different parts of the brain, these are the white matter pathways that are the sort of network or super highways of communication. I'll come back to that in a little bit. Again, these pathways, especially in the left hemisphere, look different in children who struggle to read. If you do brain activation studies where children see words or perform other reading relevant tasks, one sees reduced response, again, in this area called the fusiform word area, where print is initially treated as a special visual object. And in this area around the junction of the temporal and parietal regions, where we think sound and print come together in phonological awareness. We also see differences in the frontal cortex as well. That's a bit more complicated what that's about, but these two differences, we think, are very characteristic of the majority of children who struggle to learn how to read. So I'll quickly summarize a lot of research that's fairly convergent about these brain differences. Now, we've heard before that one of the best understood brain differences is that many children who struggle to read have a difficulty in teasing apart the sounds units of language, phonological hypothesis, and it makes it hard for them to understand that black and white strokes on the printed page are pregnant with the sounds of spoken language. And there's other difficulties that different children face as well. And it's just worth revisiting for a moment, and I know all of you in this room know this very well, but how science makes a difference. Because until the 1980s, everybody assumed reading dyslexia was primarily a visual problem, because most children at home spoke language and understood language pretty well. And then they had to hit a roadblock when they hit school, so it was the introduction of visual print that was the problem. It wasn't until the work of Bradley and Bryant especially that showed that that was not the core problem for most children, but rather the translation of spoken language into print. So let me remind you for a moment of Brain Anatomy 101, which is that in our brains there's white matter which is comprised of the myelin that sheathes axons. So here's the axon that communicates out from a neuron, and that's the white matter. I'm always impressed when you look at an MRI scan, top of the brain, bottom of the brain, how much of our brain is white matter, surrounded by this ribbon or bark of cortex, that's the gray matter. And we're able to look at that kind of the white matter and the gray matter in children with reading difficulties. This is the room we use for our youngest readers to get them ready for a scanner. It's a pretend scanner. It makes noise as it shakes, a so-called mock scanner. It's widely used in research to make children comfortable before they go into the real one. And I'm going to show you some results related to diffusion tensor imaging. It's a method to approximate the white matter organization of the brain, the area, the white matter that connects the brains into complex networks. So it helps us visualize white matter by the motion of water. Basically what happens is, again, there's this myelin sheath that surrounds axons that travel any distance. For areas that are, for white matter pathways or tracts that connect the brain across distances, there's big bundles of these myelinated axons. If you're a molecule of water floating around in the brain and you're in something like cerebral spinal fluid, you can float wherever you want. But if you come to these myelinated tracts, you have to flow around the tract. You can't flow through it any more than we can't walk through tables. We have to walk around tables. And we infer the white matter organization of an individual human brain by the flow of water that's measured in the MRI scanner. So here's an example of an individual brain. What's coded here is the direction of the flow of water that infers where the tracts are traveling. So red air tracts are traveling between the two hemispheres, right to left. Blue tracts are going up and down in the brain, cortical, subcortical. Green tracts are traveling to the front, between the front and the back. And from this individual, we can do this and measure quantitatively something about the white matter properties and organization of an individual brain. And then with my colleagues Zainab Sagan and Elizabeth Norton and Nadine Gabb, we can ask this question. If you look in the brain of a child who's in the summer before they go to kindergarten, before they will get, in Massachusetts where we did this research, the instruction for reading begins around Thanksgiving. Do we see differences in the brains of these children in relation to phonological awareness? None of these children are reading much. A few come from homes where parents are really encouraging reading and they know more words than you think, but the vast majority of children can barely read words at all. And the answer is this, and there's a much bigger data set that's published, but I'm just showing you two examples to simplify the picture. Here's the Arcuate fasciculus, that if you picked one white matter pathway, that's probably the most central to language is this one. It connects Wernicke's area and Broca's area. It's the most related to language anywhere in the brain, and we're in the left hemisphere. And we looked at scores on blended words. This is a test where we asked children, for example, they might hear ham and If you put them together, what's the word? And we hope they could blend those sounds through phonological awareness to come up with the word hammer. So there's no reading involved, there's spoken language involved. Here's a child with a low score. Here's a child with a high score. And here's the white matter pathways. The red tells you something about its properties, but even the absolute size is obviously different. So here are two children arriving into kindergarten, representative statistically of these different phonological awareness abilities. And as we followed them for first grade and now second grade, the child at the top becomes a poor reader, a dyslexic reader, and the child in the bottom becomes a typical good reader. And so this is not the only evidence for that, but let me tell you one more amazing thing. Nadine Gabb has looked at children who are born to families with a history of reading difficulty 1 month after birth. So many of these children will not have a reading problem, but disproportionately a substantial number will. And she has found that within a month of birth, one can see differences in children born to families with a history of reading difficulty in exactly the same left arcuate fasciculus. So consistent with ERP studies in infants born at risk for reading difficulty within, in some cases, hours to months after birth, but very young, brain differences are evident as early as you can measure them in children who are on trajectories for reading difficulty. So this means that we have a strong basis to know that there's a brain difference even before reading instruction begins for many children with reading difficulties. Now, what leads to this phonological awareness? As Jack pointed out, we do not have genes for phonological awareness any more than we have genes for textbooks or e-readers or anything like that, because reading is a late cultural invention. Nothing was visible until hieroglyphs, and nothing was popularly visible or widely visible until movable print. And so I want to share with you a recent finding that provokes as many questions as it gives an answer as to what might in the brain be a broader property of the brain that ultimately expresses itself as a difficulty in phonological awareness. So when we know one thing, when a person hears or sees a stimulus, like a word repeatedly, their brain responses that we measure become reduced even as performance improves. In fact, we think the reduction in brain response is about the brain learning through experience how to more efficiently process that stimulus. And so reduced response is a brain change or brain plasticity that makes perception easier or faster through experience. And a popular one in psychology is to show you a picture like this. Some of you may be familiar, and ask you to spot the dog. If you haven't seen this before, here it is. And if you have, I've ruined this for every other talk I'll ever give you, because if you ever have seen this before, you will always recognize that there's a Dalmatian, okay? And that's perceptual learning. It occurs fairly unconsciously and remarkably powerfully. And with Tyler Parashin and other collaborators, we asked this question: what does brain plasticity at the most simple level look like in adults and children who have dyslexia? We thought, based on indirect evidence from prior studies, that there might be reduction in print. Well, that's the, print is the difficult object for a poor reader. And maybe in spoken language as well, there might be reduced plasticity, because as we heard before, and as we know, the roots of reading difficulty in many children are ultimately in language. But we thought two categories that would not show reduced plasticity would be simple objects, things like tables and chairs, pictures of those, or faces of people you don't know, okay? Because even objects have names, but unknown faces have no names associated with them. So here's the first finding. Here's typical readers, and to the extent you see something in dark red, that means there's a greater reduction when a word is repeated a lot than when it is not. So how much easier does the brain find it, so to speak, to process the words that are repeated constantly? These are the areas that show reduced activation in typical readers, and you can see a much weaker response in plasticity in the people who are adults with a history and ongoing dyslexia. Now here's spoken words, so they hear tree, star, cake, every word is different, or we compare that to a condition where they hear bird, 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 bird for a while, okay? So the plasticity occurs easily for a thing that's repeated. What you see here is the marker of plasticity in typical readers, reduced activation for this repeated material, and much less of a signal, much less plasticity by this measure, much less adaptation with experience in adults with dyslexia. So that's one thing, but then here's the next thing. When we show objects, pictures like these, here's a car repeatedly shown compared to a condition where there's many different things. Here's reduced activation now in a different system, because we're out of the language system, we're out of the print system, we're into parts of the brain that respond to objects in the world. And now we can see a great reduction when objects are repeated in typical readers, but a reduced reduction in individuals with dyslexia. So this is a reduction in plasticity that's far beyond print and spoken language. And quite remarkably, the same thing for faces. My colleague Nancy Kamwisher at MIT sort of discovered the fusiform face area, the part of the brain that first responds to faces specifically and selectively. When a face is repeated a lot, there's huge plasticity or reduction in activation in typical readers, but much weaker in individuals with dyslexia. And then we thought, well, maybe this has to do with compensation that goes on across time. We're looking at adults, and in fact, adults in our studies are often university students who have accommodated quite well to the huge challenge they've been faced with dyslexia. But when we look at first and second graders, and here, we couldn't have the first and second graders be in the scanner for all the different conditions. That's too long for a second grader. But so we just did a spoken language. And again, here's the reduction or plasticity of activation in the individuals who are second graders for spoken words, and the reduced version in second graders for spoken words. And so we were quite surprised that the plasticity extended not only from print and language, but to objects and faces. And that's all the more surprising because we know that adults with dyslexia typically have no problem with faces and no problems with objects. So we don't know what the limits of this. We do know it's present early in the children. It suggests a broader brain mechanism that might be valuable for learning to read. A guess we have, and then but we still have with the mysteries. Why is the difficulty so specific to reading? One thought we have, and this goes back to the idea of evolution, is that our brains might find many different ways to address reduced plasticity. Reduced plasticity sounds bad, but plasticity is the opposite side of stability. Stability is also a great thing for brains to have, okay? So it's a sort of a balancing act between plasticity and stability. And it could be that we have many different ways through evolution to accommodate how we perceive the world. It's only when we create certain unusual demands, like reading, that the multiplicity or diversity of ways in which brains can adapt and accommodate to the world hit a roadblock that they cannot work their way around. So because recognizing faces and objects has occurred throughout our evolutionary history, perhaps there's many ways we can succeed. But there's not many ways to succeed if you can have a certain pathway required for reading. Now, one question that we often struggle with is, in what sense, beyond showing that dyslexia is a brain difference, can neuroimaging contribute to thinking about how we might improve remediation? Because most often, the most important outcome of remediation, obviously, is how well a student reads, how well a student feels about himself or herself as an agent and optimistic about his or her future, and how well they can access things like STEM to have many opportunities for their futures. So here's a study we did with Fumiko Heft where we found something that intrigued us. We know that some children make more progress than others. And we wanted to understand that. So these are older children now, 25 of them with dyslexia, age 10 to 16. And we did brain imaging them at the outset, and then we followed them behaviorally, their reading abilities, for 2.5 years. And we asked what happened. And so here's what happened. Here's single word reading. Here's text comprehension. Here's our control group. These are standardized scores. So this is not a critique of the American education system, that these children fail to improve their reading over 2.5 years. These are age-adjusted scores. So our control children are typical readers. You know, they were good readers to start with. They were good readers later on for single word reading. But within our children with dyslexia, about half of them persisted in their problem. They didn't close the gap. But half closed the gap somewhat for single words, and they closed the gap a lot for comprehension. So they were making more progress than others. And we asked if we did an activation study in their brain from originally at the very beginning of these 2.5 years, what predicted their future improvement? And quite surprisingly, what predicted their future improvement was how much they activated right prefrontal cortex when they were thinking about sounds associated with words. This is a big surprise in the sense that it's the left hemisphere that's dominant for reading in most people. So the right prefrontal cortex, the fact that, so each dot here, each red dot is an individual child who's with dyslexia. The more they turn on right prefrontal cortex to think about words and sounds, the more they improved in the next 2.5 years. So we're sort of, roughly speaking, forecasting their future. That was not true, here's the blue line, for typically reading individuals. And this made us rethink something that maybe we could have thought through better before. So some years ago, in a not well-controlled study that I was involved with colleagues at Stanford, here was activation for 10-year-olds doing a word task in the scanner in the anterior and posterior area. Absence of activation or reduced activation in children with dyslexia, and after a remediation program, growth of activation here. And so we thought, when this was published many years ago now, that this is exactly in our imagination what effective remediation does. It helps children grow the pathways that typically reading children grow. This is, we thought this is exactly what our goal is. In the left hemisphere, this is what we saw. And we weren't focused enough on what was going on at the time in the right hemisphere. So I'm showing the same data, just to show it a little bit differently. Here's the left hemisphere change. We call that normalization, just making it more like typical readers. And here's the big changes in the right hemisphere. And so that study was not well controlled, but Gabrieli did a very well controlled study. And again, changes in the left hemisphere, the typical reading hemisphere, but big changes in the right hemisphere. And this gets to this deep question, in one sense, as to whether, when we help children with dyslexia, in what sense are we trying to get them to read like most children read? And in what sense are we encouraging alternative strategies that are available to them because the typical reading pathways are simply not, for reasons we don't understand? Are we trying to make them like everybody else, so to speak? Or are we trying to let them find a different pathway that will work for them, that needs a different level of instruction and support, but will let them be more likely to succeed with effective remediation? So this is always a deep question. Are we trying to make children read the same way? Are we trying to help them reach a different way? And going back to our original data, we also used, from computer science, multivoxel pattern analysis, dividing children into those who, using all the data possible, into those who progressed and who did not. And here's the outcome of that study. The outcome was that none of the 17 behavioral measures, IQ measures, reading measures, all kinds of measures that we took, predicted reading gains 2.5 years alone or in combination. And at first we thought, well, we just didn't know the literature well enough, but in fact, if you talk to clinicians and researchers, child by child, it's very hard for them to tell which 10-year-old or 11-year-old will make substantial progress over the next few years and which ones won't. Even their beginning reading scores didn't tell us almost anything amongst these children. It wasn't that the best children made the most progress. That was not informative at all. Well, and in our best analysis in one study, we were 92% accurate in telling which child would be in the group that makes progress and which one would not be in the years to come. Now, that could be good news in a sense if the study is replicated and generalized. That could be good news if you could tell a teacher, a parent, or a student, you're in that group that's going to show substantial progress in the next 2.5 years. That'd be, that's something to know and be hopeful about. But you wouldn't want to be the neuroscientist or teacher who tells a family, oh, I'm sorry, the data suggests that your child will make, minimal progress. They'll inch along, but they won't close the gap, right? But that's important to know because here's what we're doing all the time. By generalizing findings across children who do and do not make progress, we're missing the kinds of interventions that are needed for the children who don't respond to what schools can now offer. Does that make sense? Okay. So for the children who progressed, great. Whatever the schools are doing and the parents are doing, that's good. But if the other children, the half of children who don't progress are not provided with an alternative developed treatment, remediation, or support, they will just go on to fail year after year. So we need this kind of separation to develop individualized interventions. The ones that work now for the children that responded, terrific. We need to identify those children who need a different kind of support so that we can proactively help them and not just say, gee, we tried our best, but I'm sorry it didn't work, right? So the last study I want to share with you is in collaboration with Joanna Christodoulou, who's here, my colleague, and Rachel Romeo, which is about variation in response to intervention. So we know, again, when we think about the average response to children, all kinds of medical studies, including intervention studies, always do the practically always do the studies on the average. And so they'll say, well, gee, there was an average gain. Let's say it's above kilo 0.05, terrific. And that is terrific. Actually, we could use more studies that are scientifically rigorous about interventions that work. But if each dot is a different student, well, here's some students who really benefited, some children who really benefited from this treatment, and here's some children who didn't. So what if we consider that dispersion of who benefits and who does not? In the study, we looked at 65 first and second graders with reading disability. In the summer, they came for 6 weeks, and they had 100 hours of intervention from Linda Mood Bell Seeing Stars. We had a passive control group. It's not ideal, but it was something to look at of children who didn't receive the intervention to start with, but received it later, so every family got it sooner or later. And we made a considerable effort to get a diverse sample in terms of socioeconomic backgrounds. And then I'm going to report to you both their behavioral scores and structural brain imaging before and after. So let me tell you what happened behaviorally. So here's our weighting controlled children. The bars are all below 0 because across the summer, without an intervention, their scores went down. Exactly the last thing a child needs who's behind on reading is the summer where they don't get reading instruction in school and their scores are sliding down. If we look at the children who received the intervention, it was pretty apparent that about half of the children showed benefit, but about half slid down. And in fact, if you average these two, they come to near 0, okay? But half benefited and half appeared not to benefit. One of the best predictors of who benefited, unexpectedly for us, were children who came from families of lower income. That was the single best predictor, actually. We're still working on the data. Single best predictors, children who came from families with lower income were most likely to show the benefit. But we had one more measure that we did, which is, here's a structural MRI scan. Sorry, my cursor seems to have disappeared on me. That's what they call it, a cursor, I guess. All right, anyway. But we can measure cortical thickness by taking the MRI scan and doing this, measuring the cortical thickness. And here's what we found. So here's the cortical thickness differences before and after in children who were in the no intervention control group, the waiting group. And of course, their brains showed no structural differences. We're measuring cortical thickness or brain structure. And in fact, they got slightly thinner, not statistically significant, because at this age, the cortex thins, as it will from then until young adulthood. The children who did not respond to the intervention also exhibited slightly, but not statistically significantly, thinning cortex, as typically occurs in development. But quite impressively, the children who benefited from the treatment in terms of their reading scores, everything you see here are areas that grew in thickness statistically significantly. So it's above and beyond, opposite of the trend of normal development, those children who had effective intervention at the level that we can measure it, changed their brains. So, thank you. So we think that, a lot of people think this, I believe, but that, understanding the diversity among poor readers in ways that we have not yet understood will be huge implications for discovering different kinds of interventions that are individually effective. So to summarize this, I want to point out consistent brain differences in dyslexia, that the brain differences are present basically at birth as far as we can measure them, certainly before a child arrives for his or her first reading instruction, and that supports other kinds of behavioral and screening efforts for early identification and prevention, and you heard from Jack how essential that is. And our studies that say that we can predict improvement and we can think about variation in response, that the average is useful, but there's huge variation that we need to deeply understand, really tells us about the need for personalized learning, that we have a much better chance through the combination of neuroscience, behavioral analysis, thinking about educational programs and policies, to match the needs of each child with optimal support. Different children need different things. If half of children get better with typical educational interventions, if half of children respond in a summer program, we need to understand what's different about those other half of children and what kinds of programs need to be developed around them so that all of these children can have effective programs that help them flourish and move into the world in a positive way, including STEM opportunities and everything else about their lives. Thank you very much. Yes, and then there's another hand there. Yeah.
Sorry, in your study where you're looking at change over 2.5 years, what were the ages of the children at time point 1?
That was a study, 10 to 16. It was a pretty broad range. And age was not a predictor.
Yeah, no, but...
So 16 was the end point.
Back to Dr. Fletcher's slides, and I'm just sort of running from one side of the slide to the other. He suggested that interventions for children who were diagnosed in 3rd grade or above would be less effective.
Oh yeah, so we're beyond 3rd grade.
Yeah.
But we're looking at a different granularity than we typically look at. And certainly the evidence is overwhelming that Jack Fletcher showed. So,
but in terms of your notion that some things work for some kids and they might be in one group versus another, it may actually be a function of the age of the students in the study.
Well, I don't think it is in the following sense. Let me just say that. And you're making me do the hard work of putting together data across 2 talks, right? Okay, so, but my instinct is that variation is evident all the way through, because the second study I showed you, those were 1st and 2nd graders, okay? So I don't think it's the age per se. What I think is, and the evidence is overwhelming that Jack is talking about. So I suspect it's just, we haven't looked much at the lens of individual students one by one. And of course, for science, we can't go too far that way. We can't have every story being a biography of an individual through his or her learning experience, because we can't develop consistent approaches. But I think there's a deeper variation, and I think this is what we're seeing, and we often don't track it that way. Yeah. Yes.
I just wanted to thank you for taking your research to practice in front of your legislature in Massachusetts. I know that that's not something a lot of researchers do, to come before the legislature and explain what you've been working on. But I'm in Maryland, because you're selected in Maryland, and we use your research all the time, and I just want to thank you for doing that.
Well, thank you very much. I'm so grateful you said that. I mean, that's the end point of this is to do something helpful for families and children. And I want to, I know Decoding Dyslexia is here, and I'm just huge fans of Decoding Dyslexia in Massachusetts and what these parents do to lobby on behalf, and the best sense of lobbying on behalf of the children who need that. And they've done a fantastic job in reaching out to the science community, both neuroscientists and psychologists, and we're glad to be shoulder to shoulder with parents and teachers who want to make a difference for their children. Thank you so much. think we're ready for coffee. Thank you.